Okay, so we're recording. This is the first online discussion. And let me cover the agenda for today. So the agenda for today is, oh, that's the eraser. Also, let me mute everyone. Let's see. I need to stop my share. Okay, let me mute. All right, so I'm muting everyone. And you're not allowed to unmute yourself. So, boom. Okay. So what we have going on today is we're going to cover the things Jason wanted me to cover, which is like sums and products. Oh, sorry about that. Let me see the chat. Okay, so we are having sums. We're going to cover sums and products. And we're going to cover induction. Well, at least I'll try to explain to you induction. Oops, okay. Well, it's okay. It's the first discussion back. Of course, we're going to have some technical difficulties. So I'm going to explain what sums are, and I'm going to do a couple sums because they're on my homework. They're on your homework, and you ought to see an example or two, and that'll get you all set for the homework. So what is a sum? So a sum looks something like this. You have like a big sigma, right? Yes, people in frats frats or sororities would have seen this. And then you have what's known as an index. Let's use the index k. So you have an index k, right? And it goes from n to m of a sub k, right? Where k is the index. So it looks something like this. And so at first, when you see this, right, you want to see something like this, right? So it would be, this is just the same thing as like a sub n, right? Because the index starts at n, plus a sub n plus 1 plus ... plus a sub n, right? So as an example, right, we could do something like k equals 0 to 3, right, of a sub k. And this is just the same thing. Well, it's equal to. It's just the same. This is just like a shorthand way of saying a sub 0, right? You start at index 0 plus a sub 1 plus a sub 2 plus a sub 3. So this is how you want to see it. There are some exceptions, right, to this rule, right? So the first and only one is, what if this goes backwards? Let's say I have something like k equals 3 to 0 of ak. Is this like a3 plus a2 plus a1 plus a0? And the answer is no, right? And let me explain, right? So we have a sum. Let's use the index k. We have the sum from k equals n to m of ak, right? So, and let's look at the chat. Okay, so we have this sum, right? And so what does it mean exactly? Well, sort of the official meaning can be distilled down to some lines of code. And since I guess you're all CS majors or minors or whatever, so this thing can be seen as the result of this code, right? So we're going to put the result in like result. And then we're going to execute this for loop from n to m for, let's say, k equals n. K is less than or equal to m. And I'm not gonna care. K equals k plus 1. We're gonna add equals result plus a sub k. And so basically, the value of result. So this sum is the value of result. Right? But so what if m is less than n, right? Such as like this example here, right? Well, the thing is, right, the way we define these sum notations is that we basically take these values, right, m, n, and k, and then we put them in this code, right? So if n is greater than m, right, this for loop is actually an infinite loop, right? Or actually it never, yeah, so this for loop doesn't run actually. So result just becomes 0, and that's what we take this sum to be. So something like k equals 3 to 0 of a sub k is going to be 0, right? So if you index like backwards, the sum's just going to be 0, right? So so that's actually a little bit confusing. Let me unmute everybody. And so does anyone have any questions about that?
Can you share your screen again?
Yes. Yeah, so okay. Right, so this sum can be seen as the result of executing this code, right, and taking the value of result, right? And so if n is greater than m, right, so like say you take, oh, sorry about that. You take this example where n is 3 and k is 0, right? So k will be equal to 3, and is k less than or equal to 0? It's not, right? So this loop just doesn't run, right? Because this counter always increments. We're just taking like these values and sort of plugging them in here. And so that's why backwards indexed sums are always 0.
So, no
so that's
matter,
just,
sorry, so no matter what k is and like whatever the a is, if it starts at, if it's
yeah, if it
0,
if it indexes backwards, it's always going to be 0. Yeah,
no
that's
matter
right.
what.
Mm-hmm.
Okay.
That's right. Okay.
And then wait, for product, it's gonna be 1 if it indexes backwards, right?
Yes, that's right. So I'm gonna talk about a little bit about products now, right? So product, right? So I'm gonna explain basically the same thing. So AI, right? So we're gonna index by I. You can use I, J, and K. That's usually the convention. So you want to see this. This is sort of like usually you just want to see this as like an times an plus 1 times like an plus 2 times ... times like an, right? But, right, so this, right, so what is the code for this, right? We're going to set result to 1, and then we're going to do the same for loop, right? So I equals n, I is less than or equal to m, I plus, right? And we're going to do result equals result times like the a sub I. And so if n is greater than m here, this loop doesn't run, right? So that's why you take backwards index products to be like 1. So something like this, right? So k equals 3 to 1 of k. It's not 6, right? It's not 3 times 2 times 1. It's actually 1, right? Because you're indexing, when you index backwards, this loop doesn't run. So you get something like that. So any other questions about that? No? Okay.
Someone had a question in chat.
Oh, okay. Let me pull up the chat. Let me pull up the chat. Where's the chat? Oh, yeah, yeah. So this is the product notation, right? So this let me write it. So this thing, right? If you see this thing, this is like a sum. So you should think about many things being like added together. And then when you see this big pi symbol, this is like the capital pi. This is like lowercase pi in Greek. So if you see something like this, this is like a product, right? And you should think about it as like an a1 times ... times an. So Okay, so now that we've got that out of the way, we can do maybe an example problem.
Can I ask one question real quick?
Yeah, of course. What's up?
So for the, say, initial value and the bounds, are those always going to be integers for us, or will we be, in some cases, iterating on, say, irrational?
So the index is always going to be an integer, or else like the numerical product wouldn't really make sense otherwise. It's like an index. Yeah, the indexes here are always going to be integers, right? I would say something about, actually, never mind, it's not important. So let's do an example problem. So it's going to be sort of like what you're going to see on your homework right now. So we're going to sum from I equals 2 to 5, right? And then we're going to sum from j equals I, right? So notice that the indexing here depends on the indexing before to I plus 2 of j, right? So we have this sum, and again, if we want, we can write this out like sort of in terms of like some code as we did before, right? So this sum, right? This sum's value would be stored in result, which is initially set to 0. And so we first index from I, right? From 2 to 5, from I equals 2, I is less than or equal to 5, I increments. And then the next thing, right? So for here, result is going to be added to, this thing, right? So what you want is another for loop, a nested for loop. J equals I. J is less than or equal to I plus 2. J increments. And then we're going to add J to result. And so basically, so if you want to evaluate this sum, well, you can go through all the possible ij pairs, right? You can like manually, like as a human, go through the loop and then add things to result, and you get your answer, right? But that's a little bit slow and time consuming. And you'd like maybe a better way to do this. So so that's sort of going from the outside in, right? So another way of evaluating this sum, right, is from going from the inside out. So we're going to look at like this sum first, right? So this sum is indexed by j, right? It goes from I to I plus 2, and all we're doing is summing j, right? So this thing, right, is just I plus 1 plus I plus 2, right? No matter what I is. And so this sum, right, let's bring it down. It's going to be equal to the sum of I equals 2 to 5 of 3i plus 3. So now instead of, let's see, 3 times 4 terms, instead of 12 terms, we only really have to worry about 4 terms, and we can write them out. Shit. Okay. So we can write this out, right? So it's indexed by I from 2 to 5. It's going to be like 3 times 2 plus 3 plus 3 times 3 plus 3 plus 3 times 4 plus 3 plus 3 times 5 plus 3. And I did this, I worked this problem out before I'm presenting it to here. So I know it's equal to 54. So that's sort of how you do a problem like this, right? Just evaluating a sum. So I think Jason wanted me to do another example, right? It looks similar. It looks kind of similar, but it's a little bit different, right? So I equals 2 to 5, and then j equals I to I plus 2. The same bounds, right? But instead of just j, we'll have I times j, right? So one thing we might notice, right, is that I here, right, the term in the sum here, this I doesn't depend on the index j, right? I is just depends on these things here. So what we can do is, so let me just illustrate it out. We can write this out again, right? Using j equals I from I plus 2, right? I plus 1, I plus 2. So we have like I plus 2 to 5 of, so what, I times I, right? That's the first result, plus I times I plus 1, plus I times I plus 2, right? But we can use like the distributive property, right? So, so I equals 2. Oh, this is a typo. That's okay. So we can use the distributive property on I, right? So we get I times I plus 1 plus I plus 2, right? But this is equal to I equals 2 to 5 of I times this sum, right? From j equals I to I plus 2 of j. So I didn't really solve the problem. I just showed you that you can, in this situation, right, where I doesn't depend on this index, you can pull the I sort of like out like this, right? So are there any questions about that? I just wanted to show you that if you have a number here, right, maybe like 3 or 4 or whatever, right, which doesn't depend on the index, right, then you can pull it out because you can use the distributive property. So you can get things like this. And there are some other properties related to summations. There's a handout. Well, there's a, call it discussion notes, actually. They're posted on Elms, and you can view them. So we can do the same thing. We have 2 times, well, this thing is just 3i plus 3, right? As we calculated like up there, right? So it's 2 times 3 times 2 plus 3 plus 3 times 3 times 3 plus 3. Oops. Oh, darn it. It's okay. Plus 4 times 3 times 4 plus 3 plus 5 times 3 times 5 plus 3. And so all I did here is I took the index I, right? So this thing is 3i plus 3. We did that up there. So this thing is like, so that's just I times 3i plus 3. And so all I did up here was I just plugged in I for both places. So this is like I equals 2 and whatnot. And this is I equals 5. So hopefully hopefully that'll help you do the homework on sums if you've been stuck on it or something like that. So any questions about this before we move on? No? All right, wonderful. Let's check chat. So result, okay, result because you're adding j to result. Can you only do this with iterators? Yeah, so you can pull out. Oh, is the audio muted? Give me a second. Okay, I unmuted everyone. Are there any questions? All right, no. Can everyone still hear me?
Yeah.
I can hear you.
All right, great. So, okay, so that didn't take as much time as I'd like. So here's another property that I want to point out. This one is going to be important later. So let's take a sum, right? We're going to index from k equals like 0 to n. For simplicity, we'll call it 0. And let's assume that n is greater than or equal to 0, right? Okay, so then this property is true. So we have, so the sum from k equals 0 to n of a sub k is going to be the sum from k equals 0 to n minus 1 plus a sub k, this sum, plus a sub n. So now why is that true? Well, so for this, right, well, let me try to explain why. This you can see as like A0 plus A1 plus dot, dot, dot plus AN, right? Minus 1 plus AN. And then you can sort of just group like these things together. And this whole sum right here is just the sum from 0 to n minus 1, a sub k, right? And then you can add it to a sub n. So that works when n is greater than 0. But the remarkable thing is this formula even works when n equals 0, right? So when n equals 0, let's see, when n equals 0, we have, let's see, so the sum from k equals 0 to 0 of a sub k, right? So we're going from 0 to 0 of a sub k, that's just a sub 0, right? And let's look at, damn it. Okay, so let's look at this side, right? Just to make sure that it's equal to a0. So we have this index, k equals 0 to n minus 1, right? 0 minus 1, a sub k, plus, well, a sub 0, right? But this is a backwards index, right? So it's just 0 plus a0, which is a0. So the remarkable thing is this formula always works when n is greater than or equal to 0. So this is going to be important later when we're doing induction problems. Something that might seem obvious, but has great consequences. Oh, maybe I shouldn't have erased that. It's okay. This video is recorded. All right. So are there any questions about that before we get to induction? Okay. So let's move on. So that is my tidbit about sums and products. So now we want to move on to induction, right? So Jason did a thing, I guess he posted a lecture video about him explaining induction. So the one thing that people mess up is this, with induction, is this thing like p sub n, right? And it sort of looks like a function, right? Function p, you take an n. It's a little bit more complicated than that. So yes, it is a function, right? But in what sense? So p sub n, right, is, it's a logical statement. So p of n, right, when we refer to it is, so we'll call it a proposition, right? You'll hear it called proposition a lot. But what p of n is, it's a logical statement which involves the value n. Okay, so p sub n, right? So let me give you a warning. A lot of people get this wrong. They think p sub n is a function, right? Because in induction, you prove a lot of these like formulas, right? And they think like p sub n is a formula. No, p sub n is a logical statement which involves the value n. It is either true or false. Okay. So that's a little abstract. Let me give you an example. So I'm going to let p sub n be the proposition that n equals 1, right? So this is either true or false, either n equals 1 or it doesn't. Or I can write it this way, right? So that you might not get thrown off by the formula. N equals 1. So let's tabulate, and let's just assume that n is in the natural numbers, just to make things easy. So let's tabulate like p n and p sub n. So this is where, strictly speaking, p of n is a function, right? But not in the traditional sense. It takes in a value and outputs a Boolean, either true or false. So like when n is 0, is n equal to 0? No, right? When n is 1, well, 1 equals 1, so that's true. If 2 is false, for 3 it's false, and dot dot dot, it's also false. So this is sort of what it looks like, right? When you list out, when you define this proposition P of n, right, to be the statement n equals 1, and then you can tabulate values for like 1, 2, 3, 4. Here's another example, right? So we're going to define P of n, a proposition, in this way, that 2 divides n, right? So for which things is this true? So let's work it out. So 0, does 2 divide 0? Yes, because 0 times 2 equals 0, right? And so this is true. For 1, 2 does not divide 1. Obviously, 2 divides 2, and so on, right? So yeah, so the most important thing you want to understand is that when I talk about P of n, it is just a statement that is either true or false. And for induction, okay, so for induction, we want to, so induction statements will look like something like this, right? We'll want to prove like for like n greater than or equal to like 1, P of n holds, right? Or P of n is true. So this is what you normally prove in induction. So we're not interested in like propositions where it's like maybe false here, true here, and false everywhere else, or maybe true sometimes going off and false sometimes going off, right? So the power of induction is that we can, we have like a starter value, right? And then we can say that for every value beyond the starter value, right, we have something that is true, right? So an example that Jason gave in the lecture is like for n greater than or equal to 1, the sum of the first n positive integers, so k equals 1 to n of like k, right? So this is like 1 plus 2 plus dot 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 plus n, right? So is going to be equal to n times n minus n plus 1 over 2. So this is something Jason did in the lecture. I'm not going to prove it, but you can watch it if you want. So this is sort of a statement that you might prove using induction, right? And so what is P, the proposition? Well, the proposition, right, P of n, right, it's the statement that this thing right here is equal to this thing right here. So the proposition is this statement, right? So the proposition is this equality, right? Or let me write it out because the equals gets people confused a lot. So let's call this like the left-hand side. Let's call this the right-hand side. So the left-hand side is equal to the right-hand side for like this given n, right? For n given. All right, so any questions about that? This is very important, right? So like for most people who are stuck on induction, this is like the thing they're stuck on, right? So any questions about that? That's very important.
I have a question on the, like when we're doing homeworks and stuff, should we be explicitly defining what P is, or if it's like obvious from the context of the problem, do we just say like P of n and then like P, like assume P is 0, show that the left side when substituted 0 is equal to the right side substituted 0?
So yeah, so you can define P. I think if you don't define P, like we all know what P is. It's I guess obvious from context, as you have said. So let me do a couple of examples, and I'll try to explain like the sort of format we want. Like I'll do a problem and I'll explain the formatting we want. But yeah, you're mostly right in that. Well, you can define P, or P is sort of obvious from context, as you said. So let me. Oh, sorry. Go ahead.
I think that was a cough.
Oh, okay. Sorry, I thought someone asked the question and then cut out. But if no one has any more questions, I can move on. So.
Someone says they're muted. They can't ask questions.
Oh, okay. So I unmuted everyone. Yeah, I unmuted everyone. So if you can't ask questions, then this is that's a problem on your end.
I'm unmuted now.
Okay. Caleb, you had a question?
Yes, we're allowed to define our piece of n as quantified statements, correct?
If you want. Well, it's a little tricky because P sub n is this logical statement. Usually it's a logical statement involving n, right? Or maybe you'll have like an existence statement, right? If for this n there exists some k such that, but I guess it's clear from and if you don't have a more specific example, then I'm not sure if I can really clarify that. Sorry about that.
Okay, thank you.
Yeah, no problem. Okay, so any other questions? No? Okay. So now I'm going to explain induction, right? And then I'm going to explain, so there's an induction principle, right? And then you have to apply this principle. This is basically how induction works. So there's this principle, and then you have to apply it to solve problems. So what is the principle? Okay, so let A be any natural number, right? And we're going to use natural numbers for convenience. You can actually use integers. It doesn't really matter. So let A be any natural number, right? Usually A is going to be like 0 or 1, but it can be different. The example I'm going to do is where A equals 3, and you'll see that later. So let A be any natural number, and let P sub k be a proposition, right? For all natural numbers, right? For all k in n. So P sub k, right, as we define, it's a logical statement about k for each k. Okay, suppose the following is true. So we're going to have that P sub A is true, right? So P sub A is true. Slash, P sub A holds, right? So we have this is true. And then we have that for all k greater than or equal to A, if P sub k holds, we can prove that P sub k plus 1 holds. So these two things. So P sub A is true, and for all k greater than or equal to A, if P sub k holds, we can prove that P sub k plus 1 holds. Okay, and then basically we get a statement as we've written above here, right? So we want something like this, right? So, all right, then for all n greater than or equal to A, P sub n holds, slash is true. Okay, so this is a little abstract. Let me try to explain what's going on here. So we have our number line, right? So like the claim is that for all n greater than or equal to A, P of n holds, right? So let me draw out a number line. Let's use green. Actually, let's not use green. Let's use green for like, so we have like A and A plus 1 and A plus 2 and like dot, 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 right? And so the first thing we're given is that P sub A is true, right? So for like this value, right, the proposition is true, right? And now we know from property 2 that for this thing, right, P sub A holds, right? So then we can prove that P sub A plus 1 holds, right? So we can prove this, right, by property 2. And then we can keep on going, right? Okay. And then, so basically that's how it works. So we prove that a certain base case is true. And then we prove that given like some value, right, greater than or equal to A, where the property holds, then we can prove that the property holds for the very next value, right? So we do this game of like infinite leapfrog, and then we prove that it's true for all of the K greater than A. So this is the inductive step. All right. All right, any questions about that? There are some questions in the chat. Let's see, where's the chat? Oh, damn it. Okay, so it's kind of like dominoes, yeah. I unmuted everyone, so if there is a problem with your microphone, it's probably on your end. Okay, so we have this principle of mathematical induction, and now we want to apply it to a problem, right? So how do we use this principle of induction, right, to solve problems, right? So how problem solving is going to go. Let me just outline. So how problem solving will happen. So you're going to be so you're going to be asked for like all n greater than 0, like for all integers, right? Like p sub n is true, right? So how do you prove this? Well, so what you want to do, right? First thing you want to do is prove that p sub 0 is true, right? We want to start out with the smallest value here, right? P of 0. P of 0 is true, right? And 2 is when you assume p sub k is true for any k greater than 0, and hence, and prove p k plus 1 is true. And then by this principle of mathematical induction, right, you're done, right? You are done. All right. So this is sort of an outline of what happens when you prove something by induction. You prove something called the base case, right, or the initial case. In this case, it's p sub 0, right, for this value. And for 2, you have that this, and then you prove the inductive step, right? So for any k greater than 0, we'll assume that p, oh, I wrote that a little bit badly, right? Let me rewrite that just to make sure people aren't confused. Assume for arbitrary, right? K greater than 0, pk is true. Then prove pk plus 1 is true. Okay. And then by this principle of induction, you're done. You have proven this statement. So here's the third thing I want to explain, right? We have the principle of induction and how problem solving happens using this principle of induction. And now I want to explain how 250 wants you to write your inductive proofs. Okay, so you'll start out with the, okay, so let's say, suppose we want you to prove like for all integer n greater than or equal to 0, prove p sub n is true. Something like this. So we're going to break it down into 3 steps, right? So 1, is you're going to prove the base case is true, right? So prove that P sub 0 is true. Okay. And so the second thing you want to do is what we call state the inductive hypothesis. That is, you say something like this: for arbitrary k greater than or equal to 0, P sub k is true, where P sub k is whatever proposition you're trying to prove. State the inductive hypothesis. And then it'll always go something like this: for n equals k, right? We're gonna use k, right? So actually, let me just get to that in the example. So for some k greater than or equal to 0, assume pk is true. So it's going to look something like this, where this is replaced by whatever, well, p is. It'll depend. And then 3 is you just and then 3 you assume pk, right? This statement is true, and use it to prove p sub k plus 1. And then you'll be done, right? So this is sort of how 250 wants you to write inductive proofs. And this is a little bit abstract without an example. So I'm going to do an example right now. So let's do an example. So example problem. Okay. For all integer n greater than or equal to 3, let's prove that the sum from k equals 3 to n, right? So notice why, it's from integers n greater than 3, because the index starts at 3, right? So the sum from 3 to n of 4 to the k is going to be equal to 4 times 4 to the n minus 1. It's not minus 1. It's minus like 16. Okay. 3. So I'm gonna do this. Actually, so before that, I'm gonna ask if there are any questions. So, dude, why is everyone unmute all? Unmute. Okay. Anyone have any questions?
I have a question.
Yeah.
So in high school when we did induction, we would have to have an ending statement saying that like the PK case implies P plus 1 case. Do we have to do the same thing in 250?
That's a good question. It doesn't hurt, I guess. You could say, hence we've proved. I don't actually know exactly if you have to say this or not. Implies P sub k plus 1, right? Or something like that. And then we'll be done. And hence we're done. We are done. Something like that. I'm not exactly sure whether or not you have to include this or not. But
Cool, thanks.
yeah, no problem. Sorry I couldn't give you a definite answer. Where is the chat? Let us check the chat. I noticed that. Okay. Oh, Sally's here. Sally's here. Say hi to Sally. She's the 9 a.m. discussion TA. I went to her Zoom call. So now we have this example problem, right? For all integers n greater than or equal to 3, we have to prove that this thing is equal to this thing, right? So the first thing we're going to do is we're going to, at least explicitly starting out, we should say the proposition, right? So what is the proposition, right? P sub n. So we want to prove this P of n, right? So what is P of n? Well, P of n is literally just this statement, right? This equality. So k equals 3 to n of 4 to the k equals 4 times 4 to the n minus 16 over 3. Right? Or you could say like I'm just going to use the quotes to refer to this, right? Equals, right? If it helps you see this as a logical statement and not an equation, like equals like that side, right? So like the left-hand side equals the right-hand side for like that n. So this is what we want to prove, right? And so let's do it in the 250 style, right? So first we're going to prove the base case, right? What is the base case? Where do we start? We have to start with n equals 3, right? Since that's sort of the lowest term we have. So step 1, so solution. So step 1 is the base case. So here's how I would write it. So when n equals 3, we have, we want to evaluate it at 3, right? So k equals sum k equals 3 to 3, 4 to the k, right? So this is just the sum from 3 to 3, right, with index k, and this is just equal to 4 cubed, right, which is 64, something like that. And then, so now we have to do the right-hand side because we want to show that the left-hand side equals the right-hand side, right? So the right-hand side is 4 times 4 to the n minus 16 over 3, right? And so this is 4 over 3. So when n equals 3, right? So we're just going to plug in 3, right? Sorry, that's a little terrible, but it's okay. So 4 times 64 minus 16 over 3. This is 64. It's 4 over 3 times 48, which is 64. So left-hand side is equal to the right-hand side. And hence, like P of 3 is true. So that's our base case, right? All right, step 2, right? We want to state, so what we want to do, we want to assume P sub k and use it to prove P sub k plus 1, right? So wait, we got to scroll down to, oh, shoot. Where did I put it? Oh yeah, so we want to do that, right? But first we want to state the inductive hypothesis. We want to state what PK is. And I'm having technical difficulties with my drawing pad. Okay, so step 2. Oh, that's in green. So step 2 is we want to state the inductive hypothesis. Here's how I would write it. So for n equals k greater than or equal to 3, right? Assume that, well, P sub k is true. Well, what is P sub k? Well, it is just this equality. Okay, so I'll need to use a different index, right? Or else I'm going to be like using k in the index and k on like the top here. So j equals 0 to k, right? Of 4 to the j equals 4 times 4 to the k minus 16 over 3. So this would be good enough. So notice that I introduced a variable k. I think that's what.
Why does
Jason,
j start from 0?
Oh, you're right. That is a typo. Sorry about that. It's a typo. So j equals 3, right? If j equals 0, what I just wrote isn't even true. So Okay, so this is sort of your inductive hypothesis, right? So let me explain how, because this is a writing thing. This isn't really a math thing. And so what we're doing is that for n equals this k, right? So we're introducing a variable k, right? Because in the problem we use this variable n, right? So we're sort of introducing a new variable k. It's sort of like scope. Doesn't really matter, but yeah. So in your inductive hypothesis, you want to introduce a new variable. That's just the convention. So step 3. So now we're assuming that this is true, right? And now we want to prove. All right, so we want to prove that the sum of j equals 3 to k plus 1, right? 4 to the j is going to be equal to 4 times 4 to the k plus 1 minus 16 over 3. Okay, so why do we want to prove that? Well, this equality is just precisely p to the k plus 1, right? So assuming, okay, so let me just repeat it again. So assuming this equality, right, this is our inductive hypothesis, we are going to prove this equality, p sub k plus 1. So assuming p of k, we're going to prove p of k plus 1. So let's do that right now. So how are we going to do it, right? So with things like this, what you want to do is start on one side and work your way until you get to the other side, right? So we're going to start from this side, right? So j equals 3 to k plus 1 of 4 to the j. And then we're going to use this property of sums that oh, it's going to lag a little bit when I scroll out. So this property of sums that we alluded to a long time ago, right? This thing where we can sort of pull out the last element from the rest of the sum, right? So we have this sum property here, right? So if we remember that sum property, okay, all right. We are back. Okay. So this thing, right, is equal to the sum of j equals 3 to k of 4 to the j plus 4 to the k plus 1, right, by the sum property. Mentioned earlier. So, okay. Now, what is this equal to? Well, this is equal to this, right? Because we assume that for this k, we assume that this equality is true, right? So this thing is equal to this thing by the inductive hypothesis. So we're going to write, so this is equal to 4 times 4 to the k minus 16 over 4 over 3 plus 4 to the k plus 1 by the inductive hypothesis. All right, so let's summarize what we've done so far. So we want to prove this equality given this above equality here, right? So what we've done is we've taken the left-hand side here, and then we've sort of written it in terms of this, right? So that we can use our inductive hypothesis. And my whiteboard is spazzing out again. But so this is very important. If you got this, you got induction. So are there any questions about what I did here? No? All right, great, fantastic. So now that we have this, right, getting to here is just going to be like algebra. Someone in chat asked a question. Are we going to get a cheat sheet? I hope so.
I don't think it's muted.
Okay. So, all right. So hopefully everyone can still hear me. That's the most important part. So basically, so now that we've used the inductive hypothesis, we want to get this to this, right? And that's just going to be a matter of algebra. So what we're going to do is we're going to combine this. We're going to multiply by 3 and then divide by 3 on this side. So 4 times 4 to the k minus 16 over 3. Since it's algebra, I'm going to go a little bit faster. 3 times 4 to the k plus 1 over 3, right? And then this, right, if we distribute out, it's going to be 4 to the k plus 1, right? And this is 4 squared, right? So this is minus 4 cubed, right? So since this is like 4 squared, and then you put the exponent in, and then plus 3 times 4 to the k plus 1 over 3, right? But this is like 1 times 4 to the k plus 1. So with this term and this term, we can apply the distributive property, just 1 plus 3 times 4 to the k plus 1 minus 4 cubed over 3. And then, well, we're basically done, right? 1 plus 3 is 4, right? And so we take the 4 out here, we take a 4 out here, and we take a 4 out here. And then, so then we get 4 times 4 to the k plus 1 minus 16, right? Because 16 is 4 squared over 3. So all this was algebra. All this was basically just algebra. I know someone has a question in the chat. Let me just see. Oh, in the second to last step? No, I think it's, well, I think it's fine. I don't see the problem here. So, well, okay. So yeah, so we got this, right? But this is exactly what we wanted, right? So we have this big chain of equalities, right? And then we, oh no, my pen spazzed out. We have this big chain of equalities right here. So this whole thing, right, shows that this is true. So we're done. So we're done. So we're done. All right, so let me make some remarks about the style, at least the writing part. So here I wrote some like justification for my steps. You don't have to do that at all because there are a lot of steps. I know at the beginning of the class, we had you like justify every step or something like that. Here we don't really care because you know there are a lot of steps. I guess Jason expects you to be comfortable with this, doing things like this by now. So we have, so no need to justify the steps. I only did it because it was because it clarified what I was doing. And then we have this, we have 4 lines justified by like algebra, right? So I guess that's all I want to say about like the style of how to write this inductive, proving the inductive step. Are there any questions? I'm about out of time. Well, I went over time. I actually only went about an hour, which is pretty good. But are there any questions, comments, concerns, anything like that?
To clarify, the final answer that we would put on our paper would be 4 times 4 to the k plus 1 minus 16 over 3. Like we could circle that or whatever, and that's it.
So I guess you'd write, you're right, that's a good point. So what happens, right, is, so I guess I could write, you could write some sort of justification. So we've shown, right, you know, given, well, P sub k, right, where P is as defined earlier. You don't have to write all of this out, right? I'm just writing it so it'll be good for the video. Where, so given P sub k, or P of k, where P is as defined earlier, right? We've proven P of k plus 1, right? And you might write this out, right? Or something like that to be extra precise. But so we're done, right? Like by the principle of induction. So you could write something after that. I think I used to be a grader, right? And if I saw someone put something like this, it's pretty much right. So I wouldn't take off for it, but I don't know about another grader if they might. But yeah, so this is just explaining what you're doing, right? All the actual work is like this. So any final questions about anything? Otherwise, I think I'm done. And I have, yeah, so anyone in, oh, shoot. Anyone in chat maybe? Hello? Hello? Let's open up chat. Okay. Oh, yes. So where can we find the discussion recordings? Yes, that is a good question. So I am recording this. And so what will happen is that after we finish, we're going to, I'm going to upload this whole thing, right? This whole class recording onto Panopto. And actually, so people might not know where my worksheets are. I have I have 8 of them, right? Because I skipped a number, or maybe I have 9 of them because I skipped a number. But so everything here covering the content, and then there are some exercises at the back. So basically everything I've covered is summarized in, so it's on Elms, right? And you'll find it on, there's a folder called like discussion section slides. And and the folder is 0106, that's this section. And then there's all my worksheets on there. And it's gonna, and for this class, it's going to be 250 worksheet 10.pdf. So everything summarizing what I just said in the last hour will be basically here on Elms. And on Panopto, I'm going to upload this whole recording onto Panopto. And I think it's going to be in, so Jason has created like a ton of folders, but I think my folder is looks something like this. My folder looks something like this, and you should click on it and you'll be able to see everything that we've did since class started. So I hope that wraps it up. If anyone has any other questions about anything, also I'm going to stop the recording now.
I have a really quick general question.
Yeah.
I'm not actually enrolled in your section, so when it comes to taking the quiz on Wednesday, I go to my actual TA, or do I come to your?
So for the quiz, it's online. Let's see. We want to stop the share, and I want to